Good morning, everybody. I'm Vijay Gill. I'm one of the network engineers. How's everybody today? Before we start, I would actually like to acknowledge that I am only giving this presentation on behalf of an excellent set of people, the Google Network Architecture folks, specifically Bikash. Is Paul in the audience? Paul is, wave Paul. Paul is standing by the door. This is actually most of their work. I'm just, yes, they are, I'm not giving this presentation. This presentation is being given through me. So without further ado, here we go. So my basic philosophy has always been that I'm not very sharp. So if I don't understand, chances are pretty good that I can't operate and run something. So basically, I tend to try and keep things as simple as possible so that I can understand them, which means that it actually works or has some hope of working some point. So I cut and pasted this from a very nice screed I saw about complexity of programming languages and language frameworks, except I cut programming network craziness and replaced it down with networking. So what I build is for real people like me. It is not built for PowerPoint like most of the vendors are handing out. So without further ado, this is the guiding principle. You can do 8 things really well, but the system will be extremely complex. On the other hand, you take like 2 or 3 long tails thing out, and the system becomes much more simpler. So this is the 80-20 principle. 20% of the work will need 80% of the effort. Since I am not that sharp, I try to keep it to the 80% that I can get done with 20% of the effort. So basically, an example is VLANs in a data center. So the typical solution is each service, for partitioning and security reasons, you build VLANs and then you build your clusters with a service instantiated on a set of machines and racks and firewalled off from the other services by use of VLANs. This now introduces an artificial topological constraint onto the network that you have built. The better solution, in my opinion, would be something like don't have VLANs, but to protect applications from running over each other, provide a library for communication that does lightweight encryption so that you only talk to services that have your key. And then you do key storage. And since you control the entire application stack, you can actually distribute the key and revoke the key as and when needed. So now we have eliminated VLANs in the data center. What does this mean? This means now the entire data center is one flat layer 3 network, which means that your bin packing for services across your machines and clusters is now much easier. And you will understand in a few minutes why that actually matters. So, yeah, also don't imagine things that may come down the pike. Build stuff and then rebuild later. Nothing you build the first time around is actually going to survive a year worth of production. It's all going to change anyway. So no need to build the gold-plated solution day 0. So what is Google's mission? Google's mission is to make the world's information and make it universally accessible. To that end, we have to build a fairly large network to actually get this going. These are some of the services. About half of them are still available. Other half have been killed off or have had no traction. But unfortunately, this is a stock picture. Can't change that. So here is kind of the scale we are operating at. So on average, we try to keep the trawl system is pulling in around 10 terabytes every couple of hours and distributing that, which is a fairly non-trivial amount of data. YouTube. Yeah, every time I give this presentation, the number gets deleted and added on. I think it's up to like 26 hours or 24 hours of video every minute. So in the time I've been speaking, we've added a week. And 1+ billion views a day, which is, again, a somewhat non-trivial number. How many people have done a Google search? So when you type stuff in, it says blah, 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 returned in blah, blah seconds, which is like on the order of like 200 to 300 milliseconds. So now think about what that actually means, right? You are searching a very large corpus and returning it on the order of a couple of 100 milliseconds. This means that you cannot actually go to disk to actually find the results, collate, and sort them, because they are sorted. In the meantime, there's a parallel ad auction that runs in real time every time you type in a search query. So what does this actually mean? This actually means that most of the internet is kept in RAM, which is, again, a non-trivial exercise. And how do we do that? We keep most of the internet in RAM by building these things called warehouse-scale computers. Urs Holzel and Dr. Luis Barroso had a very good booklet out on, it's at the bottom of the screen if you can read it. If you just Google for it, the data center as a computer, that actually goes into excruciating detail how these things are constructed. I will focus on the networking side of it for the most part. So this is one of our older warehouse-scale computers. This is actually what it looks like from the physical perspective. Notice a river running by it. What you don't see is the hydroelectric dam a little bit north of this in the picture. The reason we keep these in weird places is because electricity is a dominant cost in the total serving environment from an operational perspective. And transmission cost, you lose about 15 to 20% of electricity in transmission. So it is ideal to get the lowest cost of electricity to co-locate these things near hydroelectric or nuclear power plants if possible. So this is near a dam. What you see there, the first oval at the top, is the evaporative chillers. Those are fairly large. That particular thing you're looking at is comprised of 7 or 8 blocks. Each block is about half the size of this particular room. So they're actually fairly large. That is the power substation that feeds this entity. So within that computer, what do we have? It's a standard. You have some racks, you have some computers, and then you take the racks, put them together, you make a cluster, and you connect them together. So what does this actually mean for services? So this is what it looks like from a service viewpoint, right? So if you're on one server, you have access to about so many resources, about a couple of terabytes of disk. These are old numbers, by the way. They are not specific to us. If you go to a rack, within a rack, your compute domain looks like you have access to about a terabyte of RAM or more, and you have about a couple of hundred terabytes of disk. Notice the speed changes, and I'll have a graph after that. And if you go to a cluster, you get about 30 terabytes of RAM or so, which you can access around 400 microseconds. So you lose an order of magnitude every time you go one level away from the hierarchy. You gain about an order of magnitude more resources, which are then accessed about an order of magnitude slower every time you go up a level. Here is a graphical view. I'll put this up for a second so you guys can take a look at it. But the key part here is you can see the local DRAM, and these are all the notice this is a logarithmic scale on the y-axis, right? So this is actually an exponential curve. You're exponentially getting more resources the further away you go at an exponentially higher speed of access. So the question then is, why don't we buy, why do we have racks with bunch of servers in them and not go with something like a blade server with optimized compute and communication? The answer is that it doesn't actually matter. In the long run, what you see here, how many people remember Amdahl's law? This is actually pretty old school. Amdahl's law basically net says that as you distribute your computation, your speed of programming for programming that has communication increases as 1 over n. So basically, the communication overhead continues to dominate the CPU gain you get by going from 2 cores to 8 cores to 16 cores. So that is illustrated here with a communication biased benchmark. And there's nothing interesting at the internet scale that runs on less than 100,000 cores. So by the way, even if you buy these complex large blade servers for internet work, right? Keep in mind this is specific to the internet type compute I'm talking about. As the number of cores go out, there's no value in the long term in buying integrated systems. You're better off buying the cheapest hardware you can, stuffing them in and interconnecting them with the cheapest networking that you possibly can buy. And that means including things like you can't support VLANs because the chips you're using to build these systems don't have enough table space to actually properly run a full VLAN, or they don't have CPUs that can actually process a large spanning tree, so on and so forth. So the idea here is simplify. This goes back to my earlier slide where I can solve 8 problems, but really what I want to do is solve 6 of them, and then that allows me to go to commodity hardware and networking across the board, because for my work scale, specialized hardware doesn't buy me anything because my entirety of my work scale is dominated by by communication overhead. And as you can see, once you go out for about 1,000 cores, you might as well just go flat. So the problem with these concentrated compute farms is that things will fail, right? So one of the things you have is you can buy a Tandem or a Himalaya, one of these super large high availability servers. Assuming the MTBF is 30 years, you build about 10,000 of those. One of them will fail every day. And since things will fail every day, even when you are paying the very high premium for a super reliable, fault-tolerant server, you might as well write the fault-tolerant software anyway, because you have to deal with the failure. If you've gone to writing fault-tolerant software, well, in that case, then you don't really need super reliable hardware anyway, because now you can just buy the cheapest stuff that you can possibly buy and stuff them in large quantities and let your software deal with the failure rates. So here's some typical flakiness metrics. About 5% to 1% of your hard disks will die. In a typical cluster, servers will crash at least twice for no known reason. The internet is not a 5 nines fabric, obviously. We have things like sharks eating cable. We have dead horses. The dead horses story, let me explain. At a previous company, we were in an emerging economy, and the import rules were very rigorous, shall we say. So basically what we did was we imported 2 very nice boxes from our friends in San Jose and put one in the POP and had the other one in the local office. We contracted a contractor to take the box from the office to the POP when the box in the POP failed. Inevitably, the box in the POP failed. So we said, okay, we are not in peak. We can survive a couple of hours. We redirected the users away to another POP, which was, at that point, you could serve them out of that. And we said, okay, shift the box from the office to the POP. 4 hours, going across about 12 kilometers, fairly reasonable. Nothing happened. 8 hours later, nothing happened. 12 hours later, the peak happened, and we lost service. So I had to do the post-mortem. And as I was digging into the post-mortem, turns out that basically we had hired a tuk-tuk to take the box from the office to the POP. The tuk-tuk didn't show up, so the guys who were on the ground were very sharp. They hired a donkey cart, put the router on the donkey cart, and started moving the donkey cart over to the POP. Unfortunately, a truck came and hit the donkey, killing the donkey. So what they did was then they contracted for a replacement donkey, and the replacement donkey arrived a couple of hours later. So when they were harnessing the cart from the poor donkey's corpse, the thing tilted. It was a 2-wheel cart. So when they unharnessed it, it tilted over, and the router fell off, which wasn't secured properly, and fell into a large puddle of water, so destroying the router. So these kind of things happen, which is kind of like... Right, so I'm sitting here like I don't even know how to like phrase this in a postmortem, right? Like, so I basically put down the horse died and the replacement donkey caused a problem, and the guys, the executives are looking at me, and I'm looking at them, and I'm like, if the ground would open up and I would fall in, it would be quite okay. A particular one which is peculiar to the U.S. So this is not all emerging economy problems, right? The U.S. also has a very specific problem, mostly drunken hunters. So the U.S. has a lethal combination of easily available alcohol and easily available high-powered rifles. In fact, there are some people in the front row with several of them. Hi, Dave. So what you see here is an electric insulator for aerial fiber for the data center I was showing earlier. So this is up in the Pacific Northwest where hunting season opens and people take their hunting very seriously. They also take their drinking very seriously. And so when they're hunting and they are drunk, what they do is they go out in these hides, they're bored, they don't see anything. They're like, hey, look at that insulator. We'll sight our guns in and or we'll shoot it down because, well, we are bored and we are drunk. In general, they don't shoot the insulators down as much as they shoot the fiber down. Right? So basically now what you have is an outage. And on the lower picture, you see what you see here in the gentleman in the yellow. He is carrying a fiber splicing kit. Normally, you send in a Caterpillar D9 into the wilds to go to where the fiber is shot down, and then you fix the fiber. Unfortunately, as you can see from the snow, this was actually a particularly bad snowstorm. They couldn't send a Caterpillar in. So these poor guys actually had to cross-country ski 3 days into the wilderness to actually repair the fiber. Yes, so again, strange things happening to your internet is not exclusively an emerging economy phenomenon. Another thing is, in a crisis, all correlations go to 1. So what you see here is a flood with diverse fiber, not so much diverse anymore. One of the things we have seen with fiber is, especially fiber along rail paths, is that whenever there's a train derailment, if you've ever seen pictures of a train derail, what happens is the bogies pile up and then start going sideways, which acts as a very large fiber plow as it sweeps up fiber on either side of the tracks. So that's another problem here. The most reliable fiber we've found, according to our metrics at least, is fiber in gas pipelines. Because fiber in gas pipelines has this nice property that if you cut the fiber in a gas pipeline, you will die. So death is a very great focuser of the mind when you're operating a backhoe. So in general, if possible, try to get fiber next to gas pipelines because you spark them. I have seen backhoes melted from the heat of a gas pipeline fire. This is a non-trivial exercise to cut one of those. So I promised some stats. Here are some actual stats from some of our clusters. About 0.5, in a typical new cluster, right, about 0.5% machines will overheat. That's because we tend to run them pretty hot. You'll have a PDU failure. This is stuff fails. About 1,000 machines will go away. You will have a rack move, about 1,000 machines powered down, about 6 hours as they rewire and move racks around. You'll have a networking rewiring. This is about rolling 5%. This is actually fairly non-intrusive because you can actually give people heads up, I'm going to rewire this rack now, start draining, and then the services keep kind of following the sun as you roll the racks. Racks go wonky. This is normally we attribute it to DRAM or forwarding ASICs in the switches going bad. Network maintenances, you know what those are. Router reloads, router failures, simple. Interesting things is the bottom line, which is slow disks, and we still haven't figured out why, but apparently like every so often some disks which look identical have the same firmware and the same batch, just are about 5 to 10 times slower than the others, which causes problems with things like GFS, which have a bounded latency window for accessing hard disks. So they start timing those disks out. And then they come back, and then they get remastered, and they time out, they come back, they remaster it. So it causes a flakiness in the software as it tries to switch master-slave over and over again. So here is a hard drive failure bathtub curve. Notice if you're doing a petabyte sort, in each run, you will have one disk fail. Every time you run one of those. The buckets, the high, medium, low, are actually batch numbers. We have found that for the most part, disk failure rate is not correlated to vendor, OEM, firmware. They are correlated to batch numbers. This has a very important lesson for most people in their personal lives. When you go to Fry's or to Best Buy or whatever is your local supply store and buy a large number of terabyte disks and put them in your RAID 5, check they're not consecutive serial numbers because most often they will be. And so as we have seen here, the failures are correlated across batch, and RAID 5 will not help when you lose 2 disks in the same batch approximately at the same time. Not that this has not happened to me or not anything. So the design has to include the fact that you will lose disks as you're running your jobs underneath you. So that being said, the internet landscape is now starting to change. As you see, from 2000, this is the Atlas Observatory report given at NANOG 47. I just cut and pasted with permission. The warehouse scale computers are now starting to show up in the internet landscape. So the work that I'm going to be talking about is actually to scale. It is not a toy experiment. It is not a toy network. This is actually a real network. And so that just sets the stage for the next part of the talk. So in general, we are building our services with the least amount of intelligence possible at the lowest layers. So every time you go down the stack, it should be as simple as possible for that particular area of operation. And so our stack kind of looks something like this, where complexity and intelligence is mostly in the services. The rest of them provide a very solid connectivity infrastructure, and that is it. They don't do anything special at the network layer. So the service layer is highly scalable, very dynamic. They move around, as you can see, as I was talking about. The warehouse scale computers fail often. Large amounts of services are moved, drained. There are maintenance zones. So there's a large amount of churn in the connectivity topology and the traffic topology of the network. So instead of putting that intelligence in the optical layer, we elected to put that intelligence in the service layer with redirection. There's an old computer science saying that there's no problem that cannot be solved with enough layers of redirection. We have taken that and we have run with it probably to an absurd extent. This is the IP layer, which is a standardized, resilient interconnect mechanism. It does nothing else. There's no special science here. The MPLS layer just does forwarding, TE, fast restoral. Actually, most of the people who built this system are actually in the back of the room. Shout out to Joe, Scott, I see John King, Paul Schultz. Raise your hand, guys. This is your work. And then our optical layer is essentially as simple as it gets, linear point-to-point systems. No GMPLS, no fast restoral. We don't understand any of that, and the math doesn't work for our needs. So this is what our topology kind of looks like. You have the services that actually have a service topology that embeds on the things like our routers and our optical network, and the network is extremely dumb. Let me rephrase that. There is no intelligence in the network other than what's needed for MPLS level restoration. So the warehouse scale computers actually break down into two classes of traffic. One is the user traffic, things like Gmail, web search, ads, YouTube, and there is machine-to-machine traffic. This is predominantly between the data centers. Each one of them have different SLAs and different requirements, and they have different scales. The reason I gave the reliability portion of the talk earlier is to emphasize this particular fact that these things are designed to fail. As they're designed to fail, they must be able to move around within your other data centers. One of the things you can do is, for example, where you run a data center without chillers, right? So there's no direct expansion, no active cooling. You run a data center, it's pretty hot. About 5 to 10% of the time, the data center, the outside temperature or humidity is hot enough that you actually go into excursion. So at that point, what you want to do is you want to shut down low priority jobs, pull those jobs, make the CPU go down so that you can keep the data center running at half capacity or 1/4 capacity for truly crucial jobs. The work that the other jobs were doing that you've just killed because of temperature excursion, you now move to other data centers, right? To do that, you need very large amounts of bandwidth that connects those data centers together. So the scale is different. So there are basically two real ways to build it. You can build a converged network, which is what normally you would think would be the simplest answer, or you can build an overlay network. And the converged networks come in two portions. One is you have a common transport infrastructure, it's like you buy, like say, vendor X for all your optical, and you run your data center traffic in that on that infrastructure, and you run your internet scale traffic on the same infrastructure. The second way of running converged is that you run everything as a converged layer 3 or layer 2 network. This is a next generation network type where there's only one transport, there's only one layer 2 or layer 3 fabric, and then all traffic runs on that. And the second portion is overlay, where you have the same fiber paths approximately, but you have different transport, and you have different optimizations for each traffic. So the gray is spectrum for the first part, and the green is a separate spectrum from in the bottom for the overlay. So this is what a converged L1 network would look like. How are we doing on time, by the way, Dave? Okay, so we're good. This is what a converged layer 1 network looks like. You have a common physical plant. It could be either common fiber, it could be common spectrum. For example, you run your entire network in C-band or L-band, whatever. And all the classes of traffic, the M2M, which is machine traffic, the green box, the internet, AZs, ABs, all run on the same physical spectrum or physical path. And then you have your data centers, you have your egress POPs, like, for example, Ashburn, Atlanta, whatever, and then you run the entire thing on that infrastructure. This is typically how you build networks. This is typically how I've built networks before. And as I'll go into some modeling details later, so by the way, I forgot. And your data center network, which is the green box, runs, here we go, runs on the same infrastructure as well. So here's how you would build a converged layer 3 network. You have a common spectrum, which is the gray box. You have a multiplexed layer 3 system, which is the next generation network. And then you run all your traffic on that. And this is what it would look like. You see the converged, it goes to the same OEOs, it goes to the same routers, it goes to the same ports, so on and so forth. So this is what a converged L3 network looks like. Basically, the idea of a converged L3 network is very seductive. It is, you can fill in the peaks and you can fill in the troughs with, and since the SLAs are different, you can actually fill in the gaps in traffic in demand. Most traffic has a cyclic pattern to it, especially user-facing traffic. So during peak or during trough, you can fill in the gaps by using machine-to-machine traffic, which has a different SLA. Very seductive, very good on PowerPoint. So how do we build the system to carry these traffic? So there are two options. One is you can build an LSR. Actually, LSR is a red herring. You can build a transport box or a packet box with ITU integration, and you can build an LSR without ITU integration. What does that actually mean? In the first part, you see the DWDM transport takes in wavelengths, connects it directly into a framer, which talks to a packet or label fabric, and then it goes out the other side. LSR without ITU integration is actually what most of our networks are built with today. Basically, what you have is you have the DWDM transport, you have a terminal, and then you have a gray interface, which is normally 1310 nanometer. It speaks 10 gig or OC192 or whatever. You run it into a gray client interface on a router or an LSR. You do the packet add drop in the middle, and then you do the exact same thing on the other side. So basically what you're seeing is you're going through an electrical-optical, optical-electrical conversion 2 times. So this is actually what it looks like in terms of the framing and the hardware. At the top, what you have is you have your packet MPLS switch. I'm only showing one side, by the way. You have a bunch of FIFOs because you're in the asynchronous domain in the green area. Then you take your FIFOs and you take your clock and you synchronize it, and then you put it into the framers and take the framers and put it into your OTU for transport in your transmission system. The ITU integration LSR line card in the bottom actually eliminates all the FIFOs and the MACs because you're operating off of a single card. So this is a synchronous system across the board when you put it into ITU wavelengths. This eliminates about, depending on who you talk to, about 20 to 30% of the cost of getting a bit in and out of that system, because you are no longer building all the FIFOs and the buffers, MACs, so on and so forth, which are actually fairly expensive, both in board space and in power. So One way to do it is to build an overlay network. This is what an overlay network looks like. You have your internet scale optical transport, which is optimized for add drop in various places, a milk run if you would. You go to house by house, adding and dropping traffic on the optical transmission systems. And then you build a separate machine scale optical transport system, which is optimized for long distance point-to-point shots. This is mostly coherent 100 gig, coherent 40 gig systems where you can actually use fairly long haul without having to do regenerations and add drops. So a minor optimization on this system, and this is, I think Paul came up with that one. Hey, Paul, thank you. Paul said, we can put in LSRs, and LSRs, depending on where you are, will actually allow you to extend the life of your current routers by several years because you are no longer using your expensive gear for transit traffic. Transit your traffic through the simplest system possible, in which case would be an LSR that you see here. This particular, I wish I had a laser pointer, but you see this. This is the integrated LSR. So how do we actually verify out of all those cases which one actually is better from a build perspective? So we decided to actually build a model that simulated all the various scenarios, and then we had a slider. Unfortunately, I can't show you the slider because that has confidential data in it, and I can't put it on the slide. But basically, the slider allows you to vary all these parameters. These are all levers. Move the levers, move the traffic, internet traffic around, move the machine-to-machine traffic around, and a cost structure will fall out on the other side. And the key part here is using these assumptions, and they're fairly reasonable assumptions. Most of these are fed from eBay. We just went on eBay and started looking for gray market ports, as there are several people in this room here who have built large networks out of eBay. Can I see some of them? I see one. There we are. Hi, ASR. Hi, how are you doing? So this is not an unreasonable, and these are normalized to 10 gig, by the way, right? So this is not the absolute numbers. These are normalized 10 gig numbers. Why they're normalized? Because it avoids the, I can get it on eBay for like 10%, or if I go to NIMCon, I can get like a 30% discount. So just normalize them. It doesn't really matter. So here is what it looks like. Keep in mind that these are dependent on your topology and your traffic load. The key part here isn't what the absolute numbers are. It is what tells you what are some really bad ideas, right? So a really bad idea is this one, which is layer 3 converged. As you can obviously see, right, in this particular case, the junction points and dominate because all your traffic, no matter what, has to go through an OEO conversion at every junction point. That is the definition of an L3 converged network, because you want to drop some traffic off. Think of them as packet add drop multiplexers. So you're going through Atlanta, so you're going through Ashburn, and you're dropping some peering traffic off, which means that you have to have your entire data center traffic that is going from New York to Atlanta or whatever also go through the same optical electrical conversion that your peering traffic, which is dropped off, there has to go through. So obviously, this is a really bad idea. So the question is, how accurate is this model? We ran this model against our actual spends. This is not the numbers, by the way, but we ran this against our actual spend, and it's within 2 to 3% of our actual capex. So we have a lot of faith that the model is actually fairly accurate, right? So this tells us that within margin of error, L3 converged is a really bad idea for this volume of traffic, which is about your internet scale and your machine-to-machine traffic is about the same. So now what happens when you double? So here are the yellow arrows are the most optimal cost scenarios. One is the most optimal cost scenario in this model is L3 converged with ITU integration for low volumes of traffic, and the other one is with an overlay build, which is the second column. These are the cheapest. This is you separate out the machine-to-machine and the internet traffic. Now, what happens when you double your machine-to-machine traffic? Again, certain ideas are just bad. L3 converged with no ITU integration is bad in any sense. So first thing you want to do is you want to get ITU integration. Oops, come back. But the most optimal scenario within margin of error is actually I-scale and G-scale overlay with ITU integration and LSRs. So you actually build two separate networks, and those actually, for our particular scenario that we ran this model against, is the cheapest. Keep in mind that the idea here is that you actually have a model, not what the model tells you for any particular use case. Because depending on your, this is very sensitive to traffic, as you can see, obviously, and it is very sensitive to topology. You plug your own topology, and you plug your own traffic assumptions into the model, you will get an answer. The key part here is that there are some really stupid ideas, and L3 converged is one of them, right? So pretty much for any scenario, you do not want a converged network for warehouse scale computers. This is not necessarily a typical telco structure, because telco structure, there is only one class of traffic for all. There is no machine-to-machine traffic. But for people building warehouse scale computers, for the most part, a overlay network makes the most sense. So what are the conclusions we can come to this? Right, the web services actually generate more internal traffic than external traffic. Traffic volumes make cost efficiency a primary metric. Why is cost efficiency a primary metric? How many of you here have clicked on a Google ad? Notice I'm not raising my hand. There's one person in this entire room who has clicked on a Google ad. Thank you. Oh, Patrick also, too. Thank you, guys. Thank you very much. I appreciate it. The rest of you, well, you suck. Basically, the point is that since nobody clicks on Google ads, we really have to make this cheap. Otherwise, we can't afford to actually continue providing the service. Dude, nobody clicked on an ad, right? And that's how we make most of our money. I rest my case. So the key part here is cost-effective LSRs provide the simplest way to effectively stat mux ad drop traffic. Namely, you want to build these up in places where you can do large metro transit pops. So you only drop traffic to routers that actually are going to do interconnection with other people. For all your internal traffic, move away all that router ports into cheap LSR ports. And depending on your ad drop locations and a relative scale of your internal to machine traffic, either a flat DWDM LSR-based network or an LSR-based network with optical express are the ways to go for most people. And a unified end-to-end control plane at the MPLS level is good enough because you don't really want to control machine-to-machine traffic because that is all express path anyway. So the key part is there's no need for additional control plane at the optical layer. So TMPLS for us, right? Your conclusions may differ. For us, we see no value in adding any of optical restoration, liquid bandwidth modes. We prefer to keep things as simple as possible because nobody clicks on our ads, so therefore they must be as cheap as possible. That was it. Questions? I'm sure there are some people here. Hi, Leo.
Leo Bicknell, ISC. But when it is, you have this little problem that they turn off the gas and it takes like 2 days to burn out and then it has to cool down before they can fix it. So it really increases your restoration time when it is cut.
Leo is absolutely correct. The MTBF is low, but MTTR is high. You pick your poison. Any other questions? All right. Anything on the channel or tweet? There was some sort of like tweeting question going on? No? All right. Thank you very much.